The universe operates by a set of rules we thought we understood, yet scattered across the cosmos are rare structures that seem to break them entirely. This journey explores 25 of the most baffling cosmic anomalies, from matter that should not exist to gravitational forces that defy explanation. By the end, you will see the cosmos through a new lens, understanding why these rule breakers are forcing scientists to rewrite the textbooks of physics. We will uncover why entire galaxies are pulled toward an invisible point in space and what mysterious signal from the void has never been explained. What part of reality are we still missing? Our own galaxy is racing through the cosmos at an astonishing speed, pulled by a force we cannot see. This is the mystery of the Great Attractor, a gravitational anomaly of unimaginable scale located in the direction of the Centaurus constellation. It acts like a cosmic magnet, tugging not only the Milky Way but every galaxy in our local group toward a specific, hidden point in space. The sheer power of this pull defies all logical explanation based on the amount of matter we can observe. Renowned astrophysicist Alan Dressler described it as a concentration of mass that is both immense and mysterious, challenging our very maps of the cosmos. The gravitational influence we measure suggests there must be a tremendous amount of mass there, yet when we look, we find far less visible matter than needed to create such a powerful draw. This means either there is a vast amount of hidden mass we have not yet detected, or our understanding of gravity itself is incomplete on these colossal scales. Compounding the mystery is its location, which lies in a region of the sky astronomers call the zone of avoidance. This area is heavily obscured by the gas, dust, and stars of our own Milky Way's galactic plane, making direct observation incredibly difficult. It is like trying to peer through a dense fog at a distant mountain. Despite this veil, we know it is there because of its undeniable effect. Entire galaxies are streaming towards it at speeds of millions of miles per hour, a cosmic river flow that our standard models of the universe struggle to account for. Could this immense attraction be a sign of something beyond our current grasp, perhaps a hint of physics from other dimensions influencing our own? This profound gravitational puzzle naturally leads us to another cosmic oddity, one that warps the very fabric of space and time itself. While the Great Attractor pulls with an irresistible force, another anomaly presents the exact opposite problem, a staggering absence. The Boötes Void is a sphere of near-nothingness so immense it defies comprehension, stretching an almost unimaginable 330 million light-years across. Imagine a volume of space so empty that it contains only a few dozen galaxies, where a typical region of that size would hold thousands. This is not a simple pocket of darkness. It is a cosmic desert on a scale that should not exist according to our standard models of the universe. Its discovery in the 1980s sent shockwaves through the field of cosmology, forcing scientists to confront a profound gap in their understanding. Renowned cosmologist Gregory Aldering noted that voids like Boötes force us to reconsider how matter clusters and what truly drives cosmic inflation. Its sheer emptiness implies that unknown processes were at work in the early universe, processes that left behind these vast gaps. Perhaps they were seeded by peculiar quantum fluctuations in the first moments after the Big Bang, or maybe they are shaped by the subtle, relentless push of dark energy, creating bubbles of expansion within the expanding cosmos. This void is located in the direction of the Boötes constellation, and within its staggering expanse, astronomers have found only a tiny handful of isolated galaxies. These lonely star systems are like single islands in an ocean of emptiness. To grasp the scale of this isolation, Consider that if our own Milky Way were placed at the center of the Boötes Void, we would not have discovered that other galaxies even existed until the 1960s. Our entire history of astronomy would have been rewritten, our cosmic perspective utterly transformed. This emptiness is not just a curiosity, it has a tangible effect on the fabric of the universe, subtly altering the cosmic microwave background radiation, the faint afterglow of the Big Bang. How do such profound emptinesses shape the evolution of the universe around them? They stand as silent monuments to the mysteries of cosmic structure. Yet for every vast emptiness, the cosmos offers an equally bewildering density, a structure of such perfect order it seems almost artificial. Such vast emptiness stands in stark contrast to the most immense concentration of matter we have ever found. The Hercules-Corona Borealis Great Wall is a cosmic structure of such staggering proportions that it seems to defy the universe's own rulebook. This colossal filament of galaxies stretches for an astonishing 10 billion light-years, a distance so vast it represents a significant fraction of the observable universe. Its sheer size directly challenges a foundational idea in cosmology known as the cosmological principle, which states that on a large enough scale, the universe should look roughly the same in every direction, a uniform and homogeneous expanse. But the Great Wall is a glaring exception, a continent of galaxies in what should be an even ocean of matter. Astronomer John Hackiller, who helped identify it, noted that this structure pushes the limits of what we thought possible in terms of size and structure. Its discovery was itself a marvel of indirect observation. Since this behemoth is so distant, its individual galaxies are too faint to see directly. Instead, scientists mapped it by using the brilliant flashes of gamma-ray bursts, the most powerful explosions in the universe, which act like cosmic lighthouse beacons illuminating the galaxies that host them. The pattern that emerged revealed a dense, wall-like concentration of these bursts, tracing the outline of this unimaginably large structure. What makes up this cosmic leviathan? It is a web of countless galaxy clusters and superclusters, regions filled with young, active galaxies, suggesting it was a powerhouse of stellar formation in the early universe. Its existence forces a difficult question. How could something so vast form so quickly after the Big Bang? Our current models of cosmic inflation, the rapid expansion of the universe in its first moments, set a theoretical maximum size for structures. The Hercules-Corona Borealis Great Wall appears to brush against or even exceed that limit. This implies that the initial conditions of the universe may have been far more irregular than we thought, with seeds of structure planted by unknown processes, perhaps driven by the mysterious gravitational effects of dark matter or anomalies in the inflationary field itself. The debate continues over whether it truly breaks the established size limits, but its very presence suggests our cosmos is not as smooth on the grandest scales as we assumed. It hints at a universe of textures and wrinkles, of immense features woven into the fabric of space-time. If such a structure can exist, what other colossal formations lie just beyond our current vision? This confrontation with a limit of scale is nothing, however, compared to the mystery of an object that appears to defy the universe's ultimate speed limit. Even the universe's ultimate speed limit, the speed of light, has its apparent rule breakers. From the hearts of distant galaxies, we observe jets of superheated plasma erupting from monstrous black holes, and these jets seem to move at speeds that defy physics. This is the baffling phenomenon of superluminal motion, first documented in the 1960s, where blobs of material in these cosmic fountains appear to travel several times faster than light. The key word, of course, is appear. This is not a true violation of Einstein's laws, but one of the most dramatic illusions the cosmos can conjure. The effect occurs when a jet of material is blasted from a black hole at a significant fraction of light speed and is pointed almost directly at Earth. Imagine a race car on a circular track with its headlights aimed toward you in the center. As the car approaches, each subsequent flash of light has a shorter distance to travel to reach your eyes. If the car is moving fast enough, it can appear to be almost keeping up with its own light, creating the illusion that it is moving across your field of view faster than it truly is. This is the relativistic sleight of hand at play. The material in the jet is moving incredibly fast, but not faster than light. Its angle, combined with the time it takes for light to travel from different parts of the jet, compresses the apparent motion into a time frame that tricks our instruments and our intuition. Astrophysicist Roger Blandford described these jets as cosmic particle accelerators, testing the limits of Einstein's relativity in extreme environments. The energy required for this feat is unimaginable, harnessed from the intense magnetic fields and the furious spin of the supermassive black hole itself. These black holes act as gravitational engines, twisting spacetime around them and funneling infalling matter into narrow, incredibly powerful beams that can punch through entire galaxies. A prime example is the brilliant quasar known as 3C279. Observations have shown features in its jet that seem to move at apparent speeds up to 15 times the speed of light. Studying this illusion provides profound insights. It allows scientists to calculate the jet's true velocity, often over 99% of light speed, and to map the intricate dynamics of how energy is extracted from a black hole's rotation and transferred into the surrounding cosmos. These jets are among the most efficient engines in the universe, and their apparent defiance of the rules is a direct consequence of those very rules operating at their most extreme. What does this tell us about the nature of space and time? It reveals a reality where perception is warped by velocity, where the rigid framework of physics can create illusions that stretch our understanding to the breaking point. This dance of light and relativity leads us to ponder other cosmic structures that are not illusions, but are defined by something profoundly and fundamentally invisible. The very fabric of cosmic structure relies on an invisible scaffold. We have long understood that galaxies are embedded within vast, diffuse spheres of dark matter, ghostly halos whose immense gravity provides the essential glue to hold these sprawling collections of stars together. Yet the discovery of galaxies that appear to be missing this dark matter entirely shatters that fundamental picture. These are not mere curiosities. They are profound anomalies that strike at the heart of our cosmological models. One of the most startling examples is a galaxy known as NGC 1052DF2. This diffuse, ghostly galaxy, sometimes called a see-through galaxy, contains very few stars but should, according to all predictions, be dominated by a massive halo of dark matter. Instead, measurements of the motions of its star clusters and planetary nebulae revealed something astonishing. The stars were moving at surprisingly slow speeds that indicated there was simply not enough gravitational pull from unseen matter to hold the galaxy together. In a normal galaxy, stars whip around much faster, betrayed by the powerful grip of its dark matter halo. Here, that grip was barely a whisper. Astronomer Pieter van Dokkum, who led the team studying this galaxy, noted that galaxies without dark matter force us to rethink the role of this elusive substance in structure formation. How could such a galaxy even form? The prevailing lambda-CDM model, which describes our universe as containing dark energy and cold dark matter, posits that galaxies are born from the gravitational collapse of dark matter clouds. The normal matter, the stuff we can see, simply falls into these dark matter wells and condenses into stars, A galaxy without dark matter is like a building without a foundation. It should not stand. The existence of NGC 1052DF2 suggests alternative possibilities. Perhaps it formed through a unique and violent process, such as gas being violently stripped away during a galactic collision, leaving behind a dark matter-poor remnant. Or, more radically, its existence could be a clue that our understanding of gravity itself is flawed. The theory of modified Newtonian dynamics, or MUND, proposes that on galactic scales, gravity behaves differently than Newton or Einstein predicted, eliminating the need for dark matter. While MUND has its own set of challenges, galaxies like this one provide a critical testing ground. The methods used to uncover this absence are as ingenious as the discovery itself. Scientists rely on two primary techniques. The first is gravitational lensing, where the gravity of a foreground galaxy cluster bends the light from a more distant object, acting as a natural telescope. By mapping the distortion, astronomers can weigh the foreground cluster and measure its total mass, including its dark matter. The second method, used for NGC 1052DF2, is velocity dispersion. By carefully tracking the speeds of individual stars or star clusters within a galaxy, researchers can calculate the total mass required to keep them from flying apart. When the measured mass of visible stars and gas is nearly equal to the total gravitational mass, the dark matter is missing. This presents a cosmic paradox. If dark matter is the essential skeleton of the universe, how did this galaxy manage to avoid accumulating any? Its very existence implies that dark matter and normal matter can, under certain circumstances, be separated, a process that our current simulations struggle to replicate. This forces cosmologists to consider that galaxy formation is a more complex and diverse process than we ever imagined, one where the invisible hand of dark matter does not always guide the show. From galaxies mysteriously missing their dark glue, we turn our gaze to another form of cosmic order, one of improbable and breathtaking alignment. The very idea of a preferred direction in the cosmos is anathema to modern cosmology. Yet the faintest light in the universe, the cosmic microwave background, seems to be whispering that one might exist. This is the chilling anomaly known as the axis of evil. It is not a structure in space, but a pattern imprinted on the oldest light we can see, the afterglow of the Big Bang itself. When scientists created intricate maps of this radiation, they expected to find a random, featureless distribution of hot and cold spots, a final confirmation that the universe is isotropic, meaning it looks the same in every direction. Instead, they found something deeply unsettling. The fluctuations in this primordial light appear to align, however faintly, with the plane of our own solar system and the direction of our galaxy's motion. It is as if the universe's oldest fossil has our address written on it, a correlation that should be statistically impossible. Cosmologist Kate Land captured the unease perfectly, stating that this alignment could be a fluke, but if not, it points to physics beyond our current models. The name Axis of Evil was coined half in jest, reflecting how deeply this finding disturbs a foundational principle of our science. The data comes from painstaking statistical analyses of the cosmic microwave background, most famously from the European Space Agency's Planck satellite. Researchers meticulously check for any possible systematic error, any contamination from our own galactic dust, any artifact of the measurement process that could create this spooky alignment. Yet the signal persists, albeit at a low statistical significance. What could possibly link the orientation of our local planetary system to the universe's first moments? One radical suggestion is that this pattern is a fossil, a remnant of the universe's structure from a time before the Big Bang, perhaps imprinted by cosmic strings or other topological defects in the fabric of spacetime. Another, even more mind-bending possibility is that our universe is not infinite and uniform, but has a complex topology like a hall of mirrors on a cosmic scale, creating the illusion of a preferred direction. The alignment also connects to other large-scale anomalies, like the mysterious cold spot and the puzzling hemispheric asymmetry, suggesting we might be seeing different facets of a single, deeper mystery. This is not just a statistical curiosity. It strikes at the heart of our place in the cosmos. The cosmological principle assures us that we do not occupy a special location, that our view is average and representative. The axis of evil hints that we might be wrong, that there is a cosmic frame of reference after all, a subtle grain to reality against which our solar system is curiously oriented. If this preferred direction is real, it forces us to consider that the fundamental symmetries we believe govern the universe might be imperfect, or that we are seeing the shadow of a deeper layer of physics. This notion of a cosmic grain, a fundamental asymmetry woven into reality, leads us to confront another rule breaker, one that seems to defy the universe's relentless slide into disorder. Rising from the heart of our galaxy like two colossal, ghostly orbs are the Fermi bubbles, a pair of energetic structures that stretch 25,000 light-years above and below the galactic plane. These vast lobes of high-energy gamma-ray and X-ray emission form a perfect hourglass shape, a giant cosmic echo of some ancient catastrophic event. Their discovery by the Fermi Gamma-Ray Space Telescope was a complete surprise, revealing that our own Milky Way is not a quiet, stable system, but has a violent and energetic history written across the sky. Astrophysicist Douglas Finkbeiner, who led their discovery, stated that these bubbles are a testament to violent events in our galaxy's history that we do not fully understand. The sheer scale of these bubbles is difficult to grasp. They are so large that if our eyes could see their faint gamma-ray glow, they would dominate the night sky, covering a region as wide as 60 full moons. The energy required to create and sustain them is staggering, equivalent to the simultaneous explosion of 100,000 supernovae. The leading theory points to our galaxy's own supermassive black hole, Sagittarius A star, as the culprit. Millions of years ago, it might have undergone a period of intense activity, gorging on a vast cloud of infalling gas and then belching out titanic jets or winds of superheated plasma, inflating these bubbles like cosmic balloons. Yet this simple story is fraught with puzzles. The bubbles have remarkably sharp, well-defined edges, unlike the fuzzy, expanding shells of a supernova remnant. It is as if they are contained within an invisible bottle. What is preventing this incredibly hot, energetic gas from simply dissipating into the halo of the galaxy? The answer might lie in powerful magnetic fields, woven through the bubbles like a cosmic mesh, trapping the high-energy particles inside. An even more exotic possibility involves dark matter. Could the annihilation of dark matter particles near the galactic center have provided the immense, sustained energy needed to power these structures? The bubble's emission spectra provide clues, showing a specific signature of high-energy particles slamming into slower-moving gas, but the exact acceleration mechanism remains a mystery. The timing of this event is another enigma. Based on the bubble's size and expansion rate, the eruption likely occurred between 2.5 and 4 million years ago. This was a time when early hominids were already walking the Earth, a reminder that cosmic cataclysms can unfold on a timescale far removed from human history, yet leave their mark for eons. The very existence of the Fermi bubbles forces us to see our galactic home not as a serene island of stars, but as a dynamic engine capable of immense, violent outbursts that shape its evolution over billions of years. This evidence of a turbulent galactic center leads us to question the stability of space-time itself, where even the vacuum is not truly empty. Even the vacuum of space may be threaded with cosmic scars. These are cosmic strings, hypothetical flaws in the fabric of reality, predicted to be infinitely long and thinner than a proton, yet so dense that a single inch could weigh more than a mountain range. They are not made of matter, but are pure energy, cracks that formed as the universe cooled and underwent dramatic phase transitions in its first fleeting moments. Think of water freezing into ice, sometimes forming cracks and fissures as it changes state. The early universe underwent similar shifts, and cosmic strings are the one-dimensional cracks that were left behind, frozen into the structure of spacetime itself. Theoretical physicist Alexander Vilenkin described them as fossils from the universe's infancy, offering a window into fundamental forces operating at energies we can never hope to recreate. If they exist, their gravitational influence would be profound. A cosmic string would warp the space around it so severely that it could act as a perfect gravitational lens, creating identical mirror image copies of a single galaxy on either side of its impossibly thin width. Astronomers have searched for these telltale double images, but so far none have been conclusively linked to a string. Their non-detection is itself a mystery, pushing our most sensitive observatories to their limits. Another method of hunting them involves listening to the universe with pulsar timing arrays. These networks of rapidly spinning neutron stars act as celestial metronomes, their rhythmic pulses exquisitely regular. A passing cosmic string would create a ripple in spacetime, a gravitational wave that would minutely disrupt the timing of these pulses, creating a distinctive glitch in the cosmic clockwork. We have not yet heard that glitch. The energy scale required for their creation is almost incomprehensibly high, harking back to a time when the fundamental forces of nature were unified into a single, supreme force. Finding a cosmic string would be direct evidence of this grand unification, a tangible clue from the universe's first second. Some theorists have speculated that these strings could have provided the gravitational seeds around which the first galaxies coalesced, weaving the large-scale structure we see today. They might even offer an alternative explanation for some peculiar gravitational lensing effects that we currently attribute to the invisible hand of dark matter. How would their discovery reshape physics? It would provide a direct link to the highest energy scales, validate theories of cosmic inflation and symmetry breaking, and potentially rewrite the story of how structure formed in the cosmos. This search for theoretical scars leads us to a very real and equally bizarre structure, one defined not by gravity, but by a magnetic field of impossible strength. Deep within the cosmic zoo of stellar remnants exists a true monster, the Magnetar. This is a neutron star that has taken the already extreme conditions of a supernova collapse and cranked them to an unimaginable level, defined by a magnetic field of almost inconceivable power. To grasp its intensity, consider that a typical refrigerator magnet has a field of about 100 Gauss. Earth's protective magnetic field measures less than 1 Gauss. A neutron star's field is already trillions of Gauss, but a magnetar possesses a field measured in quadrillions of Gauss. At such strengths, physics as we know it breaks down completely. The magnetic field becomes a tangible force that can literally tear matter apart. It warps the very shape of atoms, stretching them into long, needle-like cylinders. A hydrogen atom in such a field would be stretched to be 200 times longer than it is wide. Matter cannot form normal chemical bonds in this environment, creating a state of material that exists nowhere else in the universe. Astronomer Crissacuvigliatu rightly called these objects laboratories for studying physics in regimes unattainable on Earth. The origin of this phenomenal magnetism is thought to lie in the star's violent birth. If a collapsing stellar core is spinning rapidly enough and possesses a particularly dense, superconducting soup of subatomic particles, its internal magnetic field can be amplified in a dynamo effect to these staggering levels. Yet the central mystery remains: why do these fields not simply decay or dissipate over time? The mechanisms sustaining them without decay are poorly understood, possibly involving strange quantum effects or the presence of exotic matter like free quarks in the star's impossibly dense core. The sheer energy stored in this magnetic field manifests in events of terrifying power. These are starquakes where the Magnetar's rigid crust, under immense strain from the twisting internal magnetic field, suddenly cracks and shifts. This releases more energy in a fraction of a second than our Sun will emit in 100,000 years. These eruptions are observed as massive gamma-ray flares. In December 2004, a magnetar named SGR 180620, located 50,000 light-years away, unleashed a flare so powerful that it temporarily ionized the upper layers of Earth's atmosphere, despite being halfway across the galaxy. It was the most brilliant transient event ever recorded from beyond our solar system, and for a tenth of a second, it outshone the full moon. Magnetars also present us with another head-scratching behavior known as the anti-glitch. Normally, a neutron star may experience a glitch, a sudden small increase in its spin rate, but magnetars have been observed to do the opposite, suddenly slowing down. This suggests that the immense magnetic field itself can act as a brake, or that vast, unseen reservoirs of superfluid inside the star are sloshing against the crust, transferring angular momentum in unexpected ways. More recently, magnetars have been linked to one of astronomy's most persistent puzzles: fast radio bursts. These incredibly brief, intense blasts of radio waves from distant galaxies appear to originate from these magnetic powerhouses, perhaps from massive starquakes or from magnetic field lines snapping and reconnecting near the surface. What happens to matter in such extreme magnetic environments is a question that pushes at the boundaries of quantum mechanics and general relativity. The field is so strong it can actually bend light, a phenomenon known as vacuum birefringence, and it warps the local space-time around the star, creating a gravitational lensing effect purely through magnetic force. These stellar anomalies challenge our very concept of what matter can endure, forcing us to rewrite the rules of stellar physics. From these magnetic extremes that warp the present, we turn our gaze to structures that challenge our fundamental understanding of cosmic age, to ancient stars that seem older than the universe itself. The Methuselah star presents a paradox that cuts to the very core of cosmic history. Designated HD 140283, this ancient sun drifts through our galactic halo just 190 light-years away, a relic from a time when the universe was in its infancy. Its composition is strikingly pure, almost entirely hydrogen and helium, with a metal content so low it confirms it must be one of the very first stars to have ever ignited. Yet when astronomers calculated its age, they were met with a result that seemed impossible: nearly 14.5 billion years. This is a full 700 million years older than the universe's estimated age of 13.8 billion years. It is a chronological impossibility, a star that appears to have been born before the cosmos itself existed. Astronomer Howard Bond, who led the precise age measurement, noted that this star forces us to refine our age-dating techniques and cosmological parameters. How can a star be older than the universe that birthed it? The resolution lies not in discarding our models, but in understanding the delicate margins of error in our cosmic measurements. The age of a star is not read from a simple birth certificate. It is pieced together from a complex puzzle of data. Astronomers use the star's measured brightness, its temperature, and its exact chemical composition to place it on a theoretical model called an evolutionary track, which traces a star's life from birth to death. The star's distance is the most critical and uncertain variable in this calculation, measured using the parallax method by the Gaia spacecraft. A tiny shift in the estimated distance can change the star's intrinsic brightness, which in turn dramatically alters its calculated age. The current best estimates, incorporating the most precise parallax data, now place the Methuselah star's age at around 13.5 billion years, just within the margin of error of the universe's age. This close call, however, highlights a profound tension. The discrepancy pushes on the levers of our fundamental constants, particularly the Hubble constant, which measures the rate of the universe's expansion. A slightly different value for this constant would mean a slightly older universe, one that could comfortably accommodate this ancient star. Alternatively, our models of how the very first stars behaved might be incomplete. Perhaps they burned their nuclear fuel more slowly or efficiently than we currently simulate, allowing them to shine for longer than our models predict. The Methuselah star is not an isolated error, it is a messenger from the cosmic dawn, compelling us to sharpen our tools and question our assumptions. It forces a conversation between stellar astrophysics and cosmology, two fields that must ultimately tell the same story of our universe's origin. This delicate dance with a temporal paradox prepares us for a different kind of cosmic extremity, a place where the absence of heat is as profound as the passage of time. Far beyond the fiery cataclysms of Magnetars, a different kind of extreme pushes the laws of physics in the opposite direction. The Boomerang Nebula holds the title as the coldest known natural place in the universe, a cosmic refrigerator where the temperature plummets to a mere 1 degree Kelvin above absolute zero. This is even colder than the faint, pervasive warmth of the cosmic microwave background radiation, the afterglow of the Big Bang itself. To exist at such a temperature, this nebula must be actively and relentlessly cooling itself, a process that defies our standard models of stellar evolution. Located 5,000 light-years away, it appears as a ghostly bipolar shape, giving it the name Boomerang, though it more closely resembles a delicate bow tie in the void. Scientist Raghvendra Sahai noted that this nebula's intense cold challenges our ideas about how stars lose mass and evolve. The secret to its profound chill lies in a phenomenon known as adiabatic cooling. Imagine using a spray can, feeling the metal container grow cold as the gas inside expands rapidly and escapes. The Boomerang Nebula is experiencing this on a cosmic scale. Its central star is expelling its outer layers at a breathtaking speed, a high-velocity stellar wind moving at over 160 kilometers per second. This causes the gas to expand so violently and so quickly that it does not have time to absorb heat from its surroundings, cooling itself in the process. The sheer scale and speed of this outflow are unprecedented, creating a frigid bubble in space. But the efficiency and persistence of this cooling are not fully explained by current theories. Why is this outflow so much more powerful and sustained than in other similar nebulae? One compelling possibility involves a hidden companion star, a binary partner whose gravitational dance could be stirring the pot, funneling the dying star's mass into these incredibly fast and focused jets. Alternatively, powerful magnetic fields, twisted and amplified by the star's final death throes, could be acting as a slingshot, accelerating material to these extraordinary velocities. The temperature itself was measured with stunning precision using the Atacama Large Millimeter Array, a collection of radio telescopes in the high Chilean desert. Astronomers observed the faint microwave glow of carbon monoxide molecules swirling within the nebula. Since these molecules absorb background radiation and re-emit it at specific wavelengths, their signal acts as a cosmic thermometer, revealing the staggering cold. This object is caught in a brief, dramatic phase of its life, transitioning from a red giant star to a planetary nebula. In this fleeting period, the star is shedding its envelope, but its core is not yet hot enough to ionize the gas and make it glow brightly. We are seeing it in its cold, pre-ionized state, a cosmic pupa frozen in a moment of metamorphosis. What can such an intensely cold environment teach us about the limits of physical laws? It is a natural laboratory for studying quantum effects and gas dynamics near absolute zero, conditions impossible to replicate fully on Earth. The nebula's very existence proves that the universe can create its own profound refrigerators, pushing matter into states of such minimal energy that they challenge our understanding of thermodynamics itself. This exploration of a cosmic deep freeze where expansion creates cold stands in stark contrast to the ultimate gravitational furnace, where compression creates a tear in the fabric of reality. Even the precise ballet of orbital mechanics holds a subtle, unexplained quirk. Spacecraft performing gravity-assist maneuvers around Earth have been recorded gaining or losing a few extra millimeters per second of velocity, a tiny deviation that defies our most careful calculations. This is the Flyby anomaly, a persistent puzzle for orbital dynamicists since the Galileo probe first exhibited the unexpected change during its Earth flyby in 1990. These are not errors in measurement, but consistent, repeatable discrepancies observed in multiple missions, including the near Shoemaker and Rosetta spacecraft. The effect is minuscule on a human scale, yet in the unforgiving precision of interplanetary navigation, where a centimeter per second can translate to being thousands of kilometers off course at Jupiter, it demands an explanation. Aerospace engineer John Anderson dedicated years to studying this, stating that these tiny discrepancies could hint at new physics or unaccounted for effects in orbital mechanics. The data comes from incredibly precise Doppler tracking, where ground stations monitor the radio signal from a departing spacecraft, detecting shifts in frequency so slight they reveal velocity changes smaller than a walking pace. During Rosetta's flyby in 2005, the anomaly was unmistakable, a small but definite speed increase that could not be blamed on atmospheric drag, solar radiation pressure, or any other conventional factor. The search for a cause has led to some exotic possibilities. Could the Earth be enshrouded in a halo of dark matter whose subtle gravitational tug provides an extra pull on passing spacecraft? Perhaps the planet's rotation drags the fabric of spacetime around with it, an effect known as frame dragging, but at a level stronger than predicted by general relativity. Others have proposed modified inertia, or even that our mathematical models of Earth's gravity field, despite being exquisitely detailed, are still missing some key feature. None of these ideas have yet provided a definitive answer. This orbital mystery serves as a humbling reminder that even in our own celestial backyard, the fundamental force of gravity may still hold secrets. If we cannot fully account for the path of a spacecraft swinging past our home planet, how can we be certain of our models on the grandest cosmic scales? This subtle tug on our probes points toward a deeper, more pervasive cosmic signal, one that echoes from the void in a rapid, repeating burst. These fleeting cosmic whispers arrive without warning, a blip of radio noise so brief it could be missed in a blink, yet within that millisecond, it unleashes more power than our sun will emit over 80 years. This is the enigma of fast radio bursts, or FRB, signals that erupt from the distant depths of intergalactic space and vanish just as quickly, leaving behind one of astronomy's most tantalizing puzzles. Their discoverer, astronomer Duncan Lorimer, called them one of the biggest puzzles in modern astronomy, pointing to extreme environments we have yet to comprehend. The first known burst, catalogued as FRB 121102, was found by sifting through archived data in 2007, a single, brilliant spike that seemed to come from nowhere. For years, astronomers debated if these were even real or just glitches in our terrestrial equipment. Then came the game changer, a burst named FRB 121102 that did something extraordinary. It repeated. Not just once, but in unpredictable, sporadic patterns, ruling out a one-time cataclysm like a star collapsing into a black hole. This repetition shattered simple explanations and opened the door to a zoo of mysterious sources. What kind of cosmic engine can turn itself on and off with such ferocious power? The leading suspects are magnetars, those neutron stars with unimaginably powerful magnetic fields. A starquake on a magnetar's surface could, in theory, release a titanic shockwave of energy, rippling out as a fast radio burst. Yet, the sheer diversity of these signals complicates the story. Some bursts are one-off events, seemingly the final death cries of a catastrophic event. Others repeat, but with no discernible rhythm, sometimes falling silent for years before erupting again in a frantic cluster of pulses. One particularly active repeater even exhibited a strange cycle, with periods of loud activity followed by quiet, hinting at an orbital motion or a precessing spin. When astronomers finally managed to pinpoint the location of a repeating burst to its host galaxy, they found it was originating from a region of intense star formation, a cosmic nursery brimming with young, massive stars that live fast and die young. This strongly implicates a youthful stellar remnant, like a magnetar, as the culprit. However, other bursts have been traced back to more sedate, ancient galaxies, suggesting multiple pathways can lead to the same phenomenal flash. The bursts themselves carry a hidden fingerprint of their long journey, a smear of different radio frequencies caused by the signal plowing through the diffuse clouds of ionized gas that fill the space between galaxies. This dispersion measure allows scientists to use FRBs as cosmic probes, mapping the otherwise invisible matter of the cosmic web, but the central mystery remains the power source. Even for a magnetar, the energy required is staggering, pushing the limits of what such an object is thought to be capable of. This has led to more exotic proposals, such as the violent interactions of cosmic strings or the collapse of strange, theoretical stars made of supersymmetric matter. Some have even dared to speculate about artificial origins, like propulsion for light sails on an interstellar scale, though most scientists consider natural explanations far more likely. The truth is, we are still listening, building more sensitive telescopes to catch these flashes in the act and unravel their secrets. What cosmic beasts are capable of such brief, universe-spanning shouts? Their very existence challenges our catalogue of celestial events and forces us to invent new physics to explain the universe's most powerful and fleeting signals. This search for the engines behind incomprehensible energy leads us to question an even more fundamental aspect of reality, the supposed constancy of nature's own rules. The very rules of reality may not be as constant as we once believed. Tucked away in the equations of physics is a number so fundamental it dictates the strength of the electromagnetic force, the very glue that holds atoms together and allows chemistry to exist. This is the fine structure constant, denoted by the Greek letter alpha. For decades, its value was considered a fixed, immutable pillar of the cosmos, a universal rule written into the fabric of space and time. Yet, observations of the most distant cosmic beacons are now shaking that pillar to its core. Light from ancient quasars, having traveled for billions of years, carries a faint suggestion that the value of alpha might be different in other parts of the universe. Physicist John Webb, a key figure in this research, stated that a varying alpha would revolutionize our understanding of the cosmos and its fundamental symmetries. His team made this startling discovery by analyzing the absorption lines in quasar spectra. As quasar light passes through vast clouds of intergalactic gas on its way to Earth, specific elements in those clouds, like iron or magnesium, imprint dark lines on the spectrum at precise wavelengths. The exact position of these lines depends critically on the value of alpha. By comparing the lines from incredibly distant quasars to the laboratory values measured on Earth, researchers detected a subtle but persistent shift. The data suggested that in one particular direction of the sky, the value of alpha was slightly smaller billions of years ago, while in the opposite direction, it appeared slightly larger. This was not a random scatter, but a potential dipole, a preferred direction in the cosmos for the laws of physics themselves. The methods used are a triumph of precision cosmology, relying on the world's most powerful telescopes, like the Keck Observatory in Hawaii and the Very Large Telescope in Chile. Yet, this is where the mystery deepens. The statistical significance of the result is tantalizing, but not yet conclusive. A fierce debate rages over whether this signal is a discovery of new physics or a colossal systematic error. Could it be that the instruments themselves introduce a tiny, wavelength-dependent distortion that mimics this effect? Perhaps our understanding of the atomic physics in these distant clouds is incomplete. The conflicting analyses from different research groups keep the issue thrillingly unresolved. If the variation is real, the implications are staggering. It would mean that the fundamental constants are not rock-solid anchors, but could change over cosmic time and space. This would provide dramatic support for theories like string theory, which posits extra dimensions of space that could cause constants to vary. It would also lend weight to the multiverse hypothesis, suggesting our universe is just one bubble in a vast foam, each with its own unique set of physical laws. How would a changing constant affect our models of the universe? A different alpha in the past would mean nuclear reactions in the first stars proceeded at different rates, potentially altering the cosmic recipe for elements essential for life. The very stability of matter itself could be called into question. This search for a drifting constant forces us to confront the most basic assumptions of science, that the laws of physics are the same everywhere and for all time. That fundamental uncertainty about the constancy of light and force finds a strange echo in another mystery, one written in the distribution of the universe's oldest light. Our own cosmic neighborhood might be far emptier than we ever realized. The KBC Void proposes that our entire local group of galaxies, including the Milky Way and Andromeda, sits inside a vast underdense bubble stretching more than 2 billion light-years across. This is not a complete emptiness like the Boötes Void, but a region where the density of galaxies and matter is significantly lower than the cosmic average. Astronomers Ryan Keenan, Amy Barger, and Lennox Cowie pieced together this picture by compiling extensive galaxy count surveys, meticulously mapping the three-dimensional distribution of matter around us. What they found was a startling deficit, a local universe that seems unusually sparse. Cosmologist Laura Mersini-Horton captured the profound implication, noting that living in a void might skew our perception of the universe's expansion rate. This is the crux of the matter. The Hubble constant, which measures how fast the cosmos is expanding, has become a source of major tension in cosmology. One method, using the cosmic microwave background, gives one value. Another method, using supernova as standard candles in the relatively nearby universe, gives a slightly faster, conflicting value. The KBC Void offers a potential solution to this puzzle. If we are indeed residing in a local underdensity, a cosmic bubble of lower density, then the space inside this bubble is expanding slightly faster than the denser regions outside. Our measurements of nearby supernova would be influenced by this local faster expansion, giving us a skewed, higher value for the Hubble constant. It is like trying to measure the average flow of a river while floating in a localized, faster-moving current. The void itself would act as a gravitational hill. The relative lack of mass means there is less gravity pulling inward, allowing the space within the void to stretch more freely compared to the denser external universe. This local effect would not be accounted for in the cosmic microwave background method, which measures the global average expansion from the infant universe. The potential confirmation of the KBC void forces a humbling realization. The cosmological principle, which states that the universe is homogeneous on large scales, might still hold true, but our local 2 billion light-year patch is not a representative sample. We are not in a special place, but we might be in a slightly unusual one, a rural pocket in a cosmos filled with metropolitan clusters. This has direct consequences for our estimates of dark energy, the mysterious force driving cosmic acceleration. If a local void is responsible for some of the apparent acceleration we measure, then the true strength of dark energy might be different than we think. What does it mean that our entire view of the cosmos is filtered through the lens of a grand local emptiness? It suggests our maps are still incomplete, and that the most fundamental numbers in cosmology may need a local correction. This contemplation of our sparse local universe shifts our focus to structures of breathtaking and improbable symmetry. Hoag's object floats in the void like a cosmic bullseye, a galaxy of such perfect circular symmetry it seems almost too beautiful to be real. Discovered by astronomer Arthur Hoag in 1950, this ring galaxy presents a formation puzzle that resists easy explanation. Its structure is breathtakingly simple, a brilliant, almost perfect ring of young, hot blue stars encircling a much older, yellower central core with a dark, seemingly empty gap cleanly separating the two. This pristine structure defies the standard model for ring galaxies, which typically involve a violent bullseye collision, where a smaller galaxy punches through the center of a larger disk galaxy, sending ripples of density through the stellar population that trigger star formation in a ring. But Hoag's object shows no signs of such a violent past. There is no visible companion galaxy that could have been the intruder, and the central core appears completely undisturbed, a quiet island of ancient stars. Arthur Hoag himself was baffled, wondering if this was the result of a unique internal instability or some long-faded event we simply have not envisioned. The ring itself is a stellar nursery, a vibrant circle of ongoing star birth, while the central core is a retirement home for aging stars, a clear indication of two distinct epochs of formation. One leading theory suggests a resonance process where certain gravitational frequencies within the original disk galaxy amplified the orbits of stars and gas, pushing them outward into that precise ring while leaving the core intact. Another idea posits that the galaxy accreted a massive cloud of intergalactic gas long ago, and this external material settled into a ring, igniting into stars. Yet the flawless symmetry remains a profound challenge. How does such a delicate structure maintain its perfect form over hundreds of millions of years without collapsing, warping, or dispersing? It exists in a state of serene isolation 600 million light-years away, a cosmic loner that evolved without the gravitational harassment that shapes most other galaxies. Its very existence suggests that galactic evolution can follow a quieter, more graceful path, one that leaves behind a masterpiece of order. This galactic marvel, a symbol of impossible symmetry, naturally draws our attention to the universe's most chaotic and energetic signatures. A single, powerful radio burst from deep space remains one of astronomy's most enduring puzzles. Known as the WOW signal, this narrowband radio emission was detected on August 15, 1977, by the Big Ear radio telescope at Ohio State University. It lasted for 72 seconds, a fleeting but intense scream in the cosmic silence that has never been heard again. The signal was so statistically significant and so perfectly matched the profile of a potential artificial transmission that astronomer Jerry Amon circled the computer printout data and famously wrote "Wow" next to it, giving the phenomenon its name. He later reflected that it was the most promising candidate for an extraterrestrial signal he had ever seen, yet it remains an enigma. The signal's characteristics are what make it so compelling. It was a narrowband signal concentrated around the hydrogen line frequency of 1420 MHz. This is a scientifically logical frequency for an advanced civilization to use for communication, as hydrogen is the most common element in the universe, making this a kind of universal channel. The signal's intensity rose and then fell in a perfect curve over the 72-second window, exactly as you would expect from a fixed source in space passing through the telescope's stationary beam. It was not modulated, meaning it carried no discernible information or pattern, just a pure, powerful carrier wave. This pointed toward a technological origin, a cosmic beacon perhaps, rather than a natural astrophysical event. Yet for all its promise, the signal's greatest mystery is its singularity. Decades of relentless follow-up observations, scanning the same patch of sky in the constellation Sagittarius, have yielded absolute silence. Nothing like it has ever been detected again from that region or anywhere else. This lack of repetition challenges our understanding of transient radio events. Natural explanations have been proposed, but each falls short. Some suggested it could have been a reflection of a human-made satellite signal bouncing off space debris, but no known satellite matched the frequency and profile. More recently, a hypothesis pointed to a passing comet, but the comets in the area at the time were not emitting at that specific frequency, and the signal's sharp, clean nature does not align with the diffuse radio glow of a comet's hydrogen cloud. The difficulties in solving this mystery are compounded by the fact that the Big Ear telescope, with its two beams, could only narrow the source down to one of two possible small areas in the sky, not a single point. We may never know what caused it. Was it a one-time malfunction of a distant, ancient spacecraft? A fleeting alignment of a natural lens that focused a faint signal from a distant galaxy for just a moment? Or was it precisely what it appeared to be, a brief, deliberate hello from a civilization that fell silent as quickly as it called out? The WOW signal stands as a ghost in the ether, a reminder that the cosmos can offer a profound question without ever providing the answer. This search for meaning in a singular radio burst leads us from the vast scales of astronomy down to the infinitesimal realm of particle physics, where another type of anomaly challenges the very building blocks of reality. A faint, persistent glow of gamma rays emanates from the very heart of our galaxy, a ghostly light that should not be there. This is the galactic center excess, a mysterious surplus of high-energy radiation detected by the Fermi Gamma-Ray Space Telescope, and its source remains one of the most debated puzzles in modern astrophysics. After meticulously modeling and subtracting all the known contributors, from the frenetic spin of pulsars to the crash of cosmic rays, this unexplained glow stubbornly remains. Its energy signature peaks at a few gigaelectronvolts, a specific fingerprint that does not perfectly match any conventional celestial object. Astrophysicist Tracy Slatire captured the dual possibility perfectly, noting that this signal could be our first glimpse of dark matter interactions, or it might reveal new aspects of stellar populations. The hunt to isolate this signal is a masterclass in cosmic forensics. Scientists must first construct an incredibly detailed model of the galaxy's diffuse gamma-ray background, a map of all the expected light from known processes. Any residual glow, any patch that is brighter than the model predicts, becomes a candidate for something new. The excess at the galactic center is just that, a broad, spherical haze of extra light concentrated where the galaxy's gravitational pull is strongest and where dark matter is predicted to be most dense. This spatial profile is a crucial clue. It looks exactly like the glow we would expect if dark matter particles were colliding and annihilating each other, converting their mass directly into energy and producing gamma rays. The leading theoretical candidate is a class of particles known as WIMP, or weakly interacting massive particles. If these elusive particles are real, the galactic center would be their prime hunting ground, a region so thick with them that they would frequently collide. Yet the case is far from closed. An alternative explanation points to a vast, unseen population of millisecond pulsars, the rapidly spinning cores of dead stars that act like celestial lighthouses, bathing their surroundings in radiation. These pulsars are faint and difficult to detect individually, and it is possible that thousands of them are clustered in the galactic center, collectively creating the apparent glow. The problem is that current surveys have not found nearly enough of them to account for the excess's widespread and smooth distribution. The debate hinges on this very smoothness. A dark matter halo would produce a seamless glow, while a collection of distinct point sources like pulsars would create a more granular, speckled appearance. Current data tantalizingly hints at some granularity, but it is not yet conclusive. If the excess is from pulsars, it would force a radical rethinking of how these objects form and congregate. If it is from dark matter, it would be one of the most monumental discoveries in the history of science, finally revealing the identity of the universe's dominant form of matter. This high-energy puzzle at our galaxy's core forces us to look outward, to question the very tools we use to measure the vastness of space and the anomalies found within the cosmic distance ladder. Our most fundamental measure of cosmic growth is splitting in two. This is the Hubble tension, a stubborn and growing rift between how fast the universe is expanding now and how fast it should be expanding based on its ancient past. One method looks back to the very dawn of time, meticulously mapping the faint ripples in the cosmic microwave background left over from the Big Bang. The Planck satellite provided this exquisitely precise baby picture of the cosmos, allowing scientists to calculate an expected expansion rate for today's universe. But when astronomers use the Hubble Space Telescope to measure the current expansion directly by observing the flicker of Cepheid variable stars and the brilliant explosions of supernova in nearby galaxies, they get a different answer. The local universe is expanding faster by about 4 or 5 kilometers per second per megaparsec. This might sound like a tiny difference, but in the precise world of cosmology, it is a glaring discrepancy that refuses to go away. Cosmologist Wendy Friedman called this tension a crisis that may lead to a breakthrough in our understanding of dark energy and the universe's evolution. The disparity persists despite ever more precise data from both camps, pointing to something profound. Either there is a subtle, unaccounted-for error in our measurements, perhaps in how we calibrate the cosmic distance ladder, or our standard model of the universe is missing a crucial ingredient. One tantalizing proposal is early dark energy, a speculative form of energy that might have briefly surged in the universe's first few 100,000 years, giving expansion an extra kick that forever altered its trajectory. Alternatively, dark energy itself might not be constant as the lambda-CDM model assumes, but could be evolving, growing stronger or weaker over cosmic time. Some physicists even suggest this could be a hint of modified gravity, a sign that Einstein's theory needs adjustment on the largest scales. The implications are staggering. If the faster local measurement is correct, it would mean the universe is expanding more quickly than we thought, which would, in turn, make it slightly younger than our current estimate of 13.8 billion years. This is not just a minor adjustment, it is a direct challenge to the entire cosmological framework that has guided our understanding for decades. How can we reconcile these two conflicting views of reality, one etched in primordial light and the other written in the stars of our contemporary cosmos? This fundamental conflict over the rate of cosmic expansion forces us to confront the possibility that our universe is not behaving as our most cherished models predict. And this search for missing energy leads us to consider the opposite end of the spectrum, to cosmic structures defined not by their explosive energy, but by their profound and puzzling silence. This repeating burst follows a rhythm that feels almost artificial. FRB 180916 is not just another cosmic screamer, it is a celestial metronome, erupting with powerful radio blasts for 4 days and then falling completely silent for 12, repeating this precise 16-day cycle with uncanny regularity. Located in a relatively nearby spiral galaxy just 500 million light-years away, this fast radio burst has become a pivotal clue in the search for their origin. Astronomer Ziggy Plunis noted that this regularity is a clue that could unlock the engine behind these mysterious bursts. The pattern itself defies simple explanations. If it were a lone, spinning neutron star, we would expect a much faster, regular pulse like a lighthouse beam. If it were a simple orbital motion, the period would likely be shorter or the signal would vary more gradually, not switch on and off like a clock. This points to a more complex cosmic dance. The leading hypothesis involves a binary system where a powerful magnetar orbits a massive companion star. The 16-day period could be the orbital cycle, and the 4-day active window might occur when the magnetar is at a specific point in its orbit, perhaps when it is closest to its companion and experiencing heightened activity. Another compelling idea involves precession, where the magnetar's spin axis slowly wobbles over a 16-day period, like a spinning top winding down. In this model, its powerful beam of radiation would only point toward Earth during a specific part of that wobble, creating the observed window of activity. The localization of this burst to a star-forming region is a crucial piece of the puzzle. These stellar nurseries are rich with the massive, short-lived stars that quickly evolve into neutron stars and black holes, providing the perfect environment for such a powerful object to form. Yet the silence phases are as telling as the bursts. What happens for those 12 days? Is the engine still running, but its signal blocked by a wind of gas from its companion star? Or is the beam of radiation simply pointed away from us, sweeping through other parts of the cosmos? This periodic quiet adds a profound layer of complexity, suggesting the source is not just erupting randomly, but is governed by a precise, repeating set of conditions we have yet to fully decipher. What kind of cosmic clock can drive such unimaginable energy with such perfect timing? The answer may lie in the intricate physics of plasma and magnetism around these stellar remnants, a realm where the rules are still being written. This search for rhythmic patterns in high-energy bursts stands in stark contrast to a different kind of cosmic unevenness, one written in the mysterious imbalance between matter and its ghostly twin. The cosmos is raining down particles of antimatter, and we have no idea why. High above the Earth, the Alpha Magnetic Spectrometer, a $2 billion particle detector mounted on the International Space Station, has recorded a persistent and puzzling surplus of positrons, the antimatter twins of electrons. This is not a subtle statistical fluctuation. It is a clear excess that grows more pronounced at higher energies, directly challenging our models of how cosmic rays are born and travel through the galaxy. Nobel laureate Samuel Ting, the driving force behind the MS experiment, stated plainly that the positron excess is a clear sign that we are missing something fundamental in cosmic ray physics. The mystery lies in the numbers. The observed flux of these antimatter particles is significantly higher than what standard astrophysical sources like supernova remnants and pulsars should be able to produce. The measurement itself is a triumph of precision. The spectrometer uses a powerful magnet to bend the paths of incoming charged particles, allowing scientists to identify their type and measure their energy with exquisite accuracy. They can distinguish a positron from an electron and track how many arrive at different energy levels. The resulting graph shows a steady rise in the positron fraction that defies expectation. One key factor in interpreting this data is solar modulation, the effect of the sun's magnetic field and solar wind, which can push lower energy cosmic rays away from the inner solar system, subtly altering the spectrum we detect. But even after accounting for this, the high energy excess remains a stubborn signal from the void. So where are all these positrons coming from? The leading conventional suspect is pulsars. These spinning neutron stars act as natural particle accelerators, and their powerful magnetic fields can create pairs of electrons and positrons, blasting them into space in a pulsar wind. Yet when astronomers tally up the potential contributions from known pulsars in our galactic neighborhood, their combined output seems insufficient to explain the sheer abundance of high-energy positrons we are detecting. This discrepancy has fueled an electrifying possibility that we are seeing the indirect signature of dark matter. Certain theoretical dark matter particles, when they collide with one another, could annihilate each other in a flash of energy, producing, among other things, pure pairs of electrons and positrons. The specific energy at which the positron excess peaks could even point to the mass of the hypothetical dark matter particle responsible. But the case is far from closed. The signal could also be produced by an unknown population of pulsars, or by more exotic astrophysical objects like microquasars, whose violent processes are not yet fully understood. This particle puzzle forces a profound question about the symmetry of the universe. Why is there so much more matter than antimatter in the cosmos? The unexpected surplus of positrons in cosmic rays is a tiny, local echo of that grandest of all imbalances, a whisper from the dark that we are only just beginning to hear. This search for missing antimatter in the cosmic wind leads us to a structure that seems to defy the most basic principle of cosmic construction. These ghostly galaxies drift through the cosmos like cosmic jellyfish, vast and diaphanous. They are known as ultra-diffuse galaxies, and their existence presents a second, even more baffling chapter in the mystery of missing dark matter. Unlike the compact stars we are used to, these UDGs are enormous, some as wide as the Milky Way, yet they contain only 1% of its stars, scattered so thinly they are almost transparent. The galaxy NGC 1052DF4 is a prime example, a celestial phantom that should not be able to hold itself together. According to our standard view, the immense gravitational grip of a dark matter halo is the only thing preventing a galaxy's sparse stars from flying apart into the void. Yet here, that essential glue is almost entirely absent. Astronomer Pieter van Dokkum observed that UDGs without dark matter are paradoxical, stating they should not exist according to our current models. Their discovery forces a profound question. How can a structure be so large and yet so fragile without disintegrating? The key to uncovering their secret lies in their low surface brightness. They are so faint that they blend seamlessly into the background glow of the night sky, making them incredibly difficult to detect. It is only with the most sensitive telescopes, like the Dragonfly telephoto array, which uses clusters of commercial camera lenses to minimize scattered light, that these cosmic ghosts have been pulled from the shadows. To weigh them, astronomers use the same technique as for NGC 1052DF2, measuring the velocities of star clusters or planetary nebulae within them. The results consistently show a shockingly low mass-to-light ratio, meaning the amount of gravity present is almost exactly accounted for by the visible stars alone, with little room left for dark matter. One leading theory suggests a violent origin within the dense environments of galaxy clusters. Here, a smaller galaxy could be rammed by intergalactic gas or harassed by the gravitational tides of larger neighbors, a process that might preferentially strip away the loosely bound dark matter halo while leaving the more concentrated stellar core relatively intact. However, this tidy explanation is complicated by the discovery of isolated ultra-diffuse galaxies floating freely in the emptiness between clusters. With no violent neighbors to rip their dark matter away, how did these isolated ghosts form? Perhaps they were born this way, emerging from unusually quiet patches of the primordial universe where dark matter simply failed to accumulate. Or maybe our understanding of gravity itself needs revision on these vast, diffuse scales. The existence of these galaxies suggests that the recipe for galaxy formation is far more diverse than we ever imagined, capable of producing structures that defy the most fundamental ingredient we thought was essential. If dark matter is not always the cosmic architect, what other forces are sculpting these fragile islands of stars? This puzzle of missing mass in the largest structures leads us to question the very nature of the stars themselves, to ancient suns that challenge our timeline of the cosmos. Deep within ancient star clusters, where most suns are aging red giants, burn stars that should not exist. Blue stragglers shine with a brilliant, youthful blue light, appearing billions of years younger than their stellar siblings in the same cluster. These celestial anomalies are the rebels of stellar evolution, flouting the established timeline that dictates older stars must cool and redden. In the globular cluster M30, for example, they stand out starkly against the redder, older population, burning hotter and brighter as if they have discovered a cosmic fountain of youth. Astronomer Francesca D'Antona described them perfectly, calling blue stragglers stellar vampires, rejuvenating themselves in ways we are still deciphering. Their secret lies in a dramatic infusion of new fuel, in the dense core of a globular cluster where stars are packed tightly together. Two aging stars can collide and merge. This violent union mixes their hydrogen fuel, stirring up the core and essentially hitting the reset button on their nuclear fusion process. The resulting single, more massive star burns hotter and bluer, masquerading as a much younger object. Another common path involves a quieter but equally profound theft. In a binary system, one star can gravitationally siphon hydrogen fuel directly from its companion. This mass transfer feeds the vampire star, allowing it to extend its life and blaze with renewed intensity, while its donor star is left depleted. The Hubble Space Telescope has provided stunning evidence for these theories, pinpointing blue stragglers in the crowded hearts of clusters where interactions are most likely. Yet the story is not so simple. Their numbers and locations do not always align with predictions. In some clusters, they are abundant in the core, but in others, they are found surprisingly in the outskirts, suggesting formation mechanisms we have not yet fully mapped. Why do some dense clusters produce fewer blue stragglers than expected? Could there be subtler forms of stellar cannibalism at work, or perhaps magnetic fields playing an unseen role in their formation? These reborn stars are more than just cosmic curiosities. They are living records of the dynamic, sometimes violent, social lives of stars. forcing us to rewrite the chapters on how stars age and interact. Their persistent, brilliant glow challenges the quiet narrative of stellar senescence, revealing a universe where stars can be granted a second act. This stellar rejuvenation through dramatic interaction finds a parallel in the invisible magnetic forces that sculpt the cosmos on a far grander scale. Floating in the primordial darkness of the early universe are colossal, glowing clouds of gas, each one a ghostly leviathan spanning hundreds of thousands of light years. These are the Lyman-Alpha Blobs, immense structures of hydrogen that shine with a specific, haunting ultraviolet light, a signature known as Lyman-Alpha radiation. Their sheer size and brilliant glow present a monumental puzzle, for they contain the energy of billions of suns, yet their power source remains shrouded in mystery. Astronomer Chuck Stadel, a pioneer in their study, described them as signposts of massive structure formation, yet their illumination mechanisms are not fully understood. The light itself is a cosmic echo, as radiation from a powerful source, like a burst of newborn stars or a voracious black hole, travels through the vast cloud. It is absorbed and re-emitted by the hydrogen atoms, scattering in all directions and making the entire gigantic volume glow. The central question is what provides the initial, tremendous blast of energy to light up such an enormous volume of space. One of the most famous examples, a blob designated LAB1, sits at a staggering redshift distance of over 3, meaning we see it as it was when the universe was only 2 billion years old. It is associated with a dense knot of young, frantic galaxies, a protocluster in the making, yet the blob's glowing gas extends far beyond the gravitational reach of these individual galaxies, forming a nebulous halo of incredible scale. To map these ethereal structures, scientists use a powerful technique called integral field spectroscopy, which allows them to capture not just an image, but a spectrum for every single point within the blob, revealing the velocity and distribution of the gas in 3 dimensions. The resulting maps show a complex, writhing structure, suggesting the gas is not static but flowing and collapsing in vast cosmic currents. The leading theories for their power source are as dramatic as the blobs themselves. It could be a frenzy of star formation so intense that the combined ultraviolet light from millions of young stars illuminates the cloud from within. Alternatively, an active galactic nucleus, a supermassive black hole at the heart of one of the galaxies, could be pouring out radiation as it consumes matter. A more exotic idea involves cold accretion, where vast rivers of primordial gas, drawn in by the gravity of a massive dark matter halo, are cooling and collapsing, releasing gravitational energy as a diffuse glow. Perhaps all 3 mechanisms are at work simultaneously, their combined efforts needed to explain the staggering luminosity. The existence of these blobs challenges our models of feedback, the process by which energy from stars and black holes regulates galaxy formation. How can such a vast and energetic structure exist without blowing itself apart or triggering star formation far more efficiently than we observe? These glowing giants are not merely isolated clouds, they are the lighthouses of the early cosmic web, marking the densest nodes where the first great structures were assembling. How do these colossal gas clouds form and shine? Their unresolved glow is a testament to the violent, energetic processes that built the universe we see today. This exploration of immense, glowing structures in the cosmic dawn leads us to consider the architecture of the cosmos itself, to the invisible filaments that connect all matter in a vast and intricate web. A mysterious current pulls entire galaxy clusters through the cosmos. This is the dark flow, a perplexing bulk motion detected across vast swaths of the observable universe, where thousands of galaxy clusters appear to be streaming in a common direction, as if drawn by a force from beyond the edge of our vision. This is not the local pull of the Great Attractor, but a motion on a far grander scale, a coordinated drift that challenges the very notion of a uniform cosmos. The effect is measured using a phenomenon called the kinetic Sunyaev-Zeldovich effect, where the faint afterglow of the Big Bang, the cosmic microwave background, is subtly distorted as it passes through the hot gas of these massive clusters. The pattern of this distortion reveals the cluster's peculiar velocity, their motion relative to the universal expansion, and the data points to a startling coherence. Cosmologist Laura Mersini-Horton captured the profound implication, stating that dark flow could be evidence for a multiverse or primordial inhomogeneities. The team led by Alexander Kashlinsky first identified this signal using data from the Wilkinson Microwave Anisotropy probe, and subsequent analyses with data from the Planck satellite have continued to show a persistent, albeit debated, signal. The statistical methods used are incredibly delicate, requiring scientists to meticulously subtract all known motions, from the Earth's orbit to the local group's drift, to isolate this faint, coherent stream. The primary challenge lies in ruling out instrumental systematics, any subtle bias or error in the telescope itself that could mimic such a large-scale pattern. Despite intense scrutiny and criticism, the signal refuses to vanish completely. If the dark flow is real, its implications are staggering. It suggests that our observable universe, a sphere nearly 100 billion light-years across, is not the entire story. Something immense, a structure or a density fluctuation on a scale we cannot see, is exerting a gravitational pull on everything within our horizon. This would violate the cosmological principle, the foundational idea that the universe is homogeneous and isotropic on large scales. One radical explanation posits that these are gravitational tides from other domains in a multiverse, neighboring bubble universes exerting their influence from outside our cosmic bubble. Alternatively, it could be a fossil imprint from the era before cosmic inflation, a primordial inhomogeneity that was stretched to superhorizon scales but never completely erased. What lies beyond the horizon, pulling thousands of galaxy clusters in a silent, relentless stream? This large-scale motion challenges the very nature of reality, suggesting our cosmos is but one piece of a far grander and perhaps infinite structure. Our journey through the cosmos has revealed countless structures that defy explanation, but the ultimate rule breaker might be reality itself. The simulation hypothesis proposes that our entire universe, with all its galaxies and laws, could be an elaborate digital construct, a simulation run by an advanced civilization. This is not just science fiction. Philosophers like Nick Bostrom have framed it as a serious, if highly speculative, possibility. He argued that if any civilization ever reaches a post-human stage capable of running vast simulations of their ancestors, then the number of simulated minds would vastly outnumber the real ones. Statistically, we might therefore be among the simulated. This idea finds eerie echoes in the very laws of physics. Take the double-slit experiment in quantum mechanics, where a particle seems to behave as a wave until it is observed, at which point it collapses into a definite particle. This profound observer effect feels less like a law of nature and more like a rendering trick, a way for the simulation to conserve processing power by only calculating definite properties when they are being looked at. Philosopher David Chalmers extended this thought, suggesting that if we are in a simulation, the laws of physics we have discovered might contain loopholes or artifacts of the underlying code. The apparent fine-tuning of the universe's fundamental constants adds another layer of intrigue. Why do the strengths of gravity and the nuclear forces and the mass of the electron seem so perfectly calibrated to allow for the existence of stars, planets, and life? It is as if the parameters were carefully set by a programmer, Searching for proof, however, plunges us into a deeper mystery. Scientists have looked for potential glitches, like a fundamental pixelation of spacetime or unexpected correlations in the cosmic microwave background that might hint at a finite underlying lattice. The challenge of unifying quantum mechanics with gravity could itself be a symptom of computational limits, a place where the simulation's physics engine struggles to reconcile two different sets of rules. Yet for all its fascinating implications, the hypothesis currently stands without empirical evidence. It is a modern philosophical puzzle that reframes our most fundamental questions. Are the cosmic anomalies we have explored merely bugs in the code of a constructed reality? This mind-bending concept brings our tour of the universe's rule breakers to a close, not with an answer, but with the ultimate question about the nature of existence itself. These 25 cosmic rule breakers, from the Great Attractor's relentless pull to the dizzying possibility of a simulated reality, reveal a universe far stranger and more wonderful than we ever imagined. Each anomaly is a testament to the incomplete nature of our cosmic map, a signpost pointing toward undiscovered physics and deeper truths. They remind us that our greatest scientific discoveries often begin not with answers, but with a profound and humbling question. This relentless pursuit of knowledge does more than just expand the frontiers of science. It reignites a primal sense of awe and wonder, connecting us to the vast, mysterious cosmos we call home. Our journey through these enigmas underscores a beautiful truth, that the universe is not a static collection of facts, but a living, breathing puzzle, constantly challenging us to look deeper. As the late, great Carl Sagan once reflected, somewhere, something incredible is waiting to be known. Which of these cosmic mysteries captured your imagination the most? Was it the silent, rhythmic pulse of a repeating fast radio burst, or the ghostly existence of a galaxy without its dark matter? Let me know your thoughts in the comments below. If you enjoyed this journey to the edges of reality, please subscribe for more deep dives into the wonders of space. Thank you for exploring with me. Keep questioning and never stop looking up.